In the ideal scenario, each thread accesses a different memory bank of shared memory. Notice how all 4 customers can be served simultaneously. This is perfect parallelism. When threads access unique banks, the GPU achieves maximum memory throughput with zero conflicts. This is what we strive for in optimized CUDA code. Now observe what happens when multiple threads request the same bank. 2 customers are waiting at bank 0, forcing serialization. Even though banks 1 and 2 are serving their customers in parallel and bank 3 sits idle, the overall warp is bottlenecked. The GPU must serve these conflicting requests sequentially, multiplying the access time by the number of conflicts. This is a bank conflict, the enemy of shared memory performance. Stride 1 represents sequential memory access, the gold standard. Each of the 32 threads accesses consecutive memory locations, mapping perfectly to our 32 banks. Remember, shared memory operates with a granularity of 4 bytes. Each bank handles 32-bit words. The greatest common divisor of 1 and 32 is 1, guaranteeing conflict-free access. This pattern completes in a single memory transaction, achieving peak bandwidth utilization. With Stride 2, we encounter our first problem. Threads now skip every other location, but notice the pattern. Threads 0 and 16 both access bank 0. Threads 1 and 17 both access bank 2. The GCD of 2 and 32 is 2, creating a two-way bank conflict. The memory system must serialize these accesses, doubling the transaction time compared to our optimal case. Stride 32 demonstrates the worst-case scenario: full serialization. Every single thread maps to the same bank, bank 0. With a GCD of 32, all threads form a 32-way conflict. The hardware has no choice but to serve each request sequentially. What should take 1 cycle now requires 32 cycles, a catastrophic 32 times slowdown. This is why power of 2 strides, especially multiples of 32, must be avoided at all costs. Here's where mathematics saves us. Stride 3 might seem arbitrary, but its GCD with 32 is 1. They're coprime. Watch how threads distribute across all banks without collision. This pseudo-random looking pattern is actually perfectly conflict-free. Any stride coprime to 32 will achieve this optimal distribution. This principle guides padding strategies. We add elements to break power of 2 relationships and create coprime strides. Multicast mode exploits a hardware optimization. When multiple threads within a warp read the same memory address, the GPU recognizes this pattern. Instead of serving each thread individually, it broadcasts the data from one bank access to all requesting threads. 4 threads reading the same location, 1 transaction. Crucially, multicast works when threads access the same address within a bank. The hardware detects identical addresses and optimizes automatically. This is why shared memory is so powerful for algorithms where threads cooperatively access the same data. Broadcast represents the ultimate sharing scenario. When all 32 threads in a warp access the exact same memory address, specialized hardware kicks in. A single read from one bank feeds all threads simultaneously. No conflict, no serialization, just one efficient broadcast operation. This is why constant values should be read from shared memory rather than recomputed. The hardware is explicitly designed for this pattern. Let's consolidate our optimization strategies. First, avoid power of two strides as they create predictable conflicts that serialize your memory access. Second, use padding techniques. Adding an extra column to your two-dimensional shared memory arrays breaks power of two alignment and creates coprime relationships. Third, maintain 4-byte alignment for your data structures as the hardware is optimized for word-aligned accesses. Fourth, leverage broadcast when threads share constant values. The hardware is your friend here. Finally, always profile with Nsight Compute. Look for the shared memory overhead metrics. They'll reveal conflicts you might not anticipate from code inspection alone. Remember, shared memory is fast, but bank conflicts make it slow. Your goal is simple: maximize parallelism, minimize serialization.